Everybody, welcome. Welcome to December 1st here in AP Calculus. I hope y'all had a good lunch break. Mine went really fast. But all right. So our check-in question for attendance today is what's the best part about December? What's the best part about December? Two people said break. Wow. All right, we got break and Christmas, sleeping during the break. Honestly, for me, it's the possibility of going back home for the holidays, Christmas food. Awesome. And I put for me, mine is I like walking by decorated houses, even though we don't decorate. I just looking at other people's decorations, all the lights and stuff. Welcome, welcome. If you just came in, we have our check-in question. Make sure you're in the right class. This is AP Calc. All right, and we have Christmas. I'm gonna put Easter egg hunts. What Evie said. Yeah, so that's nice. Israel. Yeah. All right. So let's go ahead and double check who we have here. So y'all can help me out. You could send a text if your friend is absent, so forth. And then we're gonna get started in today's stuff. So let's see. So this is who I'm missing today. I am missing wait, James? Didn't I just see James? No, James, you're here, my bad. So then we're just missing Grecia. We're just missing Grecia. So if anyone can send their text to come into class, that would be great. But yay, we got most of us here. Awesome. Welcome everybody. Thanks for sharing what y'all like about December. And then the cold weather, yes. Another part is you usually don't have to worry about fires once it hits really cold, which is good. All right, so here's our agenda, everybody. So we just had our attendance and check-in. We're going to be finishing up the Desmos we started yesterday. So as long as you log back in with your Gmail or whatever, it should put you to where you left off yesterday. And then we're going to continue that, finish it. And after that, we're going to synthesize the big ideas from that activity. I don't know if we're going to have time to do the group thing though today. I just put it in there, but if there's no time to do it, don't worry. We'll just adjust. We have a checkout question, and then our asynchronous number 13, that one's due tonight, and it's strongly related to what we're doing today on Desmos and so forth. It's pretty straightforward. And yeah. All right, let's see, there's something in the chat. All right, so it says a lot of you are very excited about this winter break coming up. Awesome. All right, so let's jump back in, everybody. So we're going back into the Desmos from yesterday. This is the same code from yesterday, and it should lock you back in to where you left off. You're going to go to student.desmos.com, and that's your code. Let me give you all some time to get yourselves back in. All right, I'm going to go ahead and join you all too. So when I go to join you, don't worry, the code should pop up. So Let's go. Let's see. Learning about, as a reminder, what we were studying yesterday was comparing original graphs with the derivative graphs. Sorry if you guys are asking for the code, it's right here. I'm just logging in back into it. There we go. There's our code. Oh no, I didn't log in with my account. I do see you on there, Rosa, though, because I gave you credit for yesterday. But that's okay, because I could just go ahead and relog in, and then I'll just tell you which slide to start off with, and that's okay if it didn't save for you. Yeah, that's okay, because I see your name here from yesterday, but don't worry, we could just continue off from there. You could just log in with a new name, that's okay. All right, so I think most of us are kind of in. Let's see. Yep. Yeah, we're just, and then we're just, I think, waiting on Viviana. I know, Rosa, you have to just log in, and then let's see. Anyone else we're waiting on? And then Sophia's not here today. And then Evie. We're just waiting on Evie to join us. And I think we left off on slide number 8. We're on slide number 8. And that was in respect to answering this one here, which was y'all were asked to predict what happens, or like where the zeros of the derivative function would be. And most of you had predicted that it would be at these 3 locations. So at this maximum, at this minimum, and at this minimum. But the surprising thing was when you looked at the graph, let me go to student version. When you looked at the graph, what had ended up happening is at those sharp points, the derivative kind of like broke off. It's like there's a gap at those sharp points. But at this original point where you all guessed there was a 0 was indeed true. So that one's just a new thing that we kind of left off with yesterday. So based on what you see now, we're going to go ahead and jump into slide number 9. So for slide number 9, this is just for y'all to just openly think about it. We're going to know why the derivative looks like that at the sharp corners later on in our lessons. But for today, let's just reflect. So what makes the derivative's behavior at x equals -2, so right here is x equals -2, different from the corner points at x equals -4 and at x equals 0? Go ahead and put down your thoughts. Like, what do you think makes it so different? And maybe why do you think there's a gap happening there? All right, I think I'm still waiting on a few more to join us there on slide 9 for us. Don't worry, I'll anonymize it once you all get your ideas in. I think I'm waiting, Evie, if you could join us on slide number 9. So given that, what do you think makes it so different there at those sharp corners? And I know 2 of you, like yesterday, had mentioned like, oh, I think it was the derivative wouldn't exist there or something like that. So 2 of you kind of had an idea of why that was happening. So I'll let you guys write and give a few time for that. And let me start to anonymize your names. Oh, sorry. So there was a thing that says, can we go over slide number 7? My bad, I just seen this. So slide number 7. Oh, I don't think we looked at what y'all said, huh? So on slide number 7 was basically, this is for those who requested for me to go over slide number 7, but you could totally get on slide 9 and start writing your thoughts. So the question was, where is the slope of the tangent line 0? So again, tangent line is like, you want to imagine that you're drawing tangent lines down on this curve. And then you want to see where the tangent line is horizontal. So I could see right here, if I was to draw tangent lines, my tangent line would be horizontal at this spot. So it's like tangent line. Oh, it's in red. Hold on. Do blue. Say this is a tangent line. Let's say this is another one. So far, it's looking pretty straight. Here's another one. Then I have to go over to this side and make a tangent line. This side becomes horizontal right here. So that's where it's 0. And you have to just keep making your tangent lines. And oops. And the question was, where are they 0 at when you're imagining drawing these tangent lines? Maybe some of you, as you can see when I'm drawing these tangent lines, can kind of see what's happening there at the corners. Like, does the tangent line become ever 0 at these corners when I was drawing these lines? This right here should be horizontal. And again, the tangent line slope is 0 when the line itself is horizontal. So that's just a review. And then this were some ideas that you all had said for this one. Again, most of you, if you look at the responses, let me take out my drawings. Most of you, if you look at the responses, had thought that all the zeros are at the maximums and minimums, right? If you look at these pictures, you all thought those were where the 0 locations were. But to our surprise, when you look at the graph itself on slide number 8, you see that you don't get zeros at these sharp points. You get like a gap in your graph instead. So that's what's different. And number 9, you're just being asked to reflect on why do you think that's the case, or why do you think it's different there? So I hope that was helpful. Yes, the slope is 0 when the tangent line is horizontal. Like if you're imagining that you're drawing these tangent lines on the curve, once it gets like horizontal, that's when the slope is 0. All right, so we have some ideas. So the derivative's behavior is different because the slope might not exist. This could be since it comes to an abrupt end and goes to a different slope. So that's interesting. I definitely, okay, so I'm highlighting Pierre's response. It says this could be since it comes to an abrupt end and goes into a different slope. And this could create like an asymptote, which makes the tangent line break up. So I do agree that the slope does change drastically. For example, if I'm drawing the tangent line on this side, oops, it's supposed to be my straight line. If I draw my tangent line right here, as I'm tracing the graph, in order to move on to the next part of the curve, my tangent line has to come this way. Notice how it doesn't really like flatten out when it does that transition. It does change abruptly. It goes from a negative to a positive slope. So I agree with what Pierre said here. Maybe that's why there's that gap in your graph. And so maybe the derivative, doesn't exist, is what they said right here. So that's interesting. It could be an idea. It could be the reason why. Let's see if anyone else said anything similar. What makes it so different is the dot isn't on the line. And then for this one, I'm not sure. This is for Mary's response. I'm not sure the dot means the purple one. Are you talking about derivative one or the original? The fact that the slope changes so fast. So 2 people had that idea. The slope is changing very quickly at those corner points. And then Emery, like the behavior, I'd like to know like what do you mean by the behavior? And then we have some incomplete thoughts there. Go ahead and finish your thoughts for Shirley if you're still writing, y'all. I'm just pointing out some responses that are worth noting. All right, and then Grace says, what makes it so different is that it's non-existent at -4 and 0, maybe because there's no slope there, question mark. The point is positive y rather than those points being negative and having a sharp point. Hmm. All right, go ahead and finish up your thoughts because you definitely want to for your full credits. I'll give you all more time if you still want to take a look at this. Okay, some more of your thinking, it's because it's that sudden change of slope. So James, it's, by the way, y'all, if you want to know who your name is, it's on your screen, like on your Desmo screen, it shows like what your anonymized name is, by the way, just so in case you're curious. Hmm. All right, y'all, make sure you finish up your thoughts here and your sentences. Again, especially if you haven't yet finished, because you are able to go back in this and finish up your responses because I opened up the windows for everything. We're gonna now move on to the next part. We're gonna be trying to match original graphs with derivative graphs. So we're gonna try to like apply what we've learned. So it says, now that you've explored some functions and their derivatives, you're ready to start at least making some matches, even if right now the understanding is like it's barely there, right? It's barely there, but we're gonna try to explore a bit. So on the next page, you're gonna match derivatives with the graphs of the original function. So this is going to be, y'all, slide 11. So right here, slide 11, what you're going to do is you're going to match original graphs with their derivatives. And what you see, so right now what you're seeing is your names, right? Look, if I unanonymize, here's your real names, right? This is everyone's real name. But of course, I'm going to anonymize it. Okay, Juan already has a match. So, or Pierre. Okay. So just so you could see, this is Juan. Okay, you're already exposed. So this is Juan's first match, right? Now, it says that the red function is the original function and the green one is the derivative. So I want you to notice that when you're making these matches, just because you already got a match in, so I'm just using yours as an example, I want you to notice that in this original graph, whenever there's a maximum, the derivative function has a 0 there. So notice how this is a minimum, by the way, it has a 0, and then there's a maximum, it has a 0 at that same location. I also want you to notice that when the graph is decreasing, the derivative graph is below the x-axis. When the graph is increasing, notice that the derivative graph is above the x-axis. Then when the graph is decreasing, the derivative is below the x-axis. So notice those patterns there. So that's why this right here is a correct match. And then you all are free to ask questions, by the way, because I could help give tips and clues. I also want to point out, hey, watch out for this sharp point. Remember what happens when we try to find the derivative of a sharp point. So just pay attention to that too. All right, y'all, try to start matching, and then I'll try to give tips as I see y'all matching and stuff. Okay, and then here you could check out like where some matches are incorrect. All right, maybe I could give some feedback here to Sun Young. So let's see which one would be incorrect. So I don't know if this was made on purpose or not, but I could see that this right here is incorrect. The reason for that is because whenever you have a sharp corner, your derivative graph should have a gap. So you'd have to look at which one of the green graphs has like a gap or a break in its graph, because that's what happened. Whenever there was a sharp corner, we had a break. So that's my feedback for Sun Young. All right. Great. A lot of us are getting there. Then we're still missing a few of you on getting started. Few of you, so Ada, Grace, Andre, Maria, Arthur, Diego. Y'all want to go, and Gertrude. Y'all want to go ahead and get started so that you could get your credit. Okay, so if you are on your phone, y'all, try to log back in with your computer. And here's the code up here. So you're going to go to student.desmos.com and then you're going to put this code right here. For those who were saying they're on their phone, go ahead and pause and you could log out, and or you could keep yourself logged in and log in with your computer. Or you know what? You don't have to log out of here. Keep yourself logged in on Zoom, but on your computer, go ahead and log into the Desmos and you're able to complete it. You know what I mean? Like you could still just log into the Desmos and here's the code. Yeah, you don't have to like log out at all. Try and see if that works, y'all. All right. Oh, okay. We already got two who are finished. Awesome. And feel free if anyone has any questions, put it in the chat. Maybe some of your peers who are done can help. So I'm just taking a look at Mary Ellen's. So Mary Ellen, just for some feedback, I don't know if this is just because you're organizing your stuff, but each red function has to match with a green. So for example, if you have two reds here, you want to try to take out one red. And for example, right here, this isn't a match because these are both derivative graphs. You want to make sure it has one red, one green. So that's just some feedback. All right, let's take a look here. So I'm looking at James's. James, like not our James. This is a James, a fake name James. I don't know who this is, but let's take a look here. So to give some feedback, because it says there was two incorrect. Okay, so my feedback is for this card. This is for James Maxwell. So for this one, if your original graph is red and it's sloping downward, that means that slope is always negative, yet your derivative graph is at a constant 0. You want to actually match this one up with a graph that has a constant negative number, not at a constant 0. So that's my feedback for this card match right here. All right, let's check out Diana. So for Diana, my feedback is going to be, let's take a look here. So this one, I originally talked about whenever you have a sharp corner, you want to match this red one up with a green graph that has a gap in its graph. That relates to what we're talking about today, that whenever there's a corner, the derivative graph actually has like a gap. It kind of doesn't exist at that corner. So that's my feedback for this match that you have right here. For this one, and again, this is for Diana. For this one, you want to make sure that if you have a maximum point in your original function or a minimum, right? So right here, this is your original because it's in red. Original graph has a minimum at this location. So that means that must correspond to your derivative graph, which it does, right? Like, okay, I see that. But this derivative graph looks like it's recording another max or another minimum at a second point, which the original function doesn't have. So that would be my feedback for this one here. So you would just want to make sure that you're matching those up. All right, we have more. All right, we got Felix has adjusted the cards. We have 1, 2, 3. 3 are finished. A lot of you are in the right path. Maybe I could give some feedback to Grigory. So let's see, what would be the 2 incorrect ones? Let's see, this looks good. We have max, min, decreasing, increasing, decreasing. All right, so this one's for Gregory. So this card I can immediately see is incorrect. The reason for that is, again, I gave the same feedback to another student, but your original graph is a line and it's always sloping downward, negative slope always. That means the tangent line slope is always negative and it's a negative constant. So if you look at your derivative, it's not at a negative constant. This is just a decreasing line. But the derivative of that should be like a negative number. It should be a straight line. So that would be my feedback for matching this red one. And I would kind of look at this card for you to help. So something needs to be swapped between these two cards. Oh, sorry, there's something in the chat. Sorry. Oh, can I get clarity? Yeah, just let me know which one you are, because I don't know whose name is who right now at the moment. Oh, okay. So we got Emery. And the question was, third card, if my third card to the right matches or not. This one here, I mean, it looks correct since it's green. So if you look here, oh, no, Emery right here, the third card, I mean, they're all green so far. So far you have correct matches for Emery. So you just need to match 2 more pairs. So far all of these are accurate. These are accurate. And this one too. Now you just want to match the parabolas there to these lines. Third card. Which one? Because they're both right. See, so this is for Emery. It says so far that the matches you have are correct. So the first 4 matches you have are correct. All right, awesome. And I see Diana made some adjustments. And we're still missing a few people on getting started. You want to make sure that you go back in and get this started. And let me just check out Diana's here. So for Diana, my feedback is, so right here what we have, this is the original function right here that has like a sharp point right here. That should correspond to a break in the graph. So my suggestion is you switch this one to match with this one. This one should not have a break in its graph because it's a smooth curve. The derivative exists at all points because it's smooth. So I would match the sharp pointed one with the derivative graph that has a discontinuity in it. So that's my feedback. All right, awesome. We're getting there, everybody. All right. I think Emery's almost there too. Let me know if anyone else would like further feedback because I'm happy to like right now real time give you feedback, and I apologize for those who are already ready. Thank you so much. Maybe y'all have some tips as well when you're doing your matches. Okay, so let's go ahead. I'm gonna go ahead and end and give feedback for Diana. Again, if you're Ada, Andre, Maria, Gertrude, Diego, Arthur, Olga, you wanna make sure you do your matches because I can't give you full credit unless you do. So great, so great. I'm liking these matches so far for Diana. I guess I have some feedback for, let me just move this out the way. It's a little bit hard. Okay, so my feedback, if I look at this card, like I'm just looking at this one I just touched. If my red function is my original function, right? I know if I'm to draw tangent lines on here, the tangent line becomes horizontal right here at this maximum point. Whenever there's a max or min, that means the derivative becomes 0 there. That means this graph should correspond to a 0 at that location, but it doesn't. Notice how it's not going down to the x-axis at that location. So that would be my feedback, because notice if I was to draw tangent lines along this curve, the tangent line is positive, positive, becomes 0 right here, then negative, negative, and then forever negative. So what that means is the graph is above the x-axis, the derivative graph is above, becomes 0, then goes below. So I would switch this card to match a line that behaves that way. And it has to be a green line that behaves that way. You might have to move some stuff so you could see which one it is. And then likewise for this graph right here, the original graph has a minimum. So I know that there should be a 0 at this location. So this right here, derivative match is not accurate because this is saying the derivative is 0 everywhere. That's what this line is saying, which is not the case for this original graph. All right, let's have a few minutes on this. Great. And then we have Alan's almost there. Most of us are in green. All right. Most of us are in the green there. And then let's check out your last matches for the, yeah, Diana, it's the ones I originally said. So it's this one's incorrect. And which other one was incorrect? And these two right here. One of these has to be, no, wait, this one's right. Sorry. This one and this one. So there might have to be a swap made for that one. All right, cool. So hoping everyone got to do their card matches. Now, so some of you kind of had to do some trial and error. Some of you were maybe listening to like the feedback I was giving everybody, right? Let's go ahead and jump into the next portion of this activity, which is, and wait, we only have 11 of y'all. Who is missing from participating with us? Come join us, everybody, because you don't want to miss out on your credit. And then for those who had the computer issue, you want to make sure you join in with your laptop so you could complete this activity. So if you're on slide 12 here, sorry, let me go to slide 12. Share your ideas. So in the following challenge, so there's going to be challenge slides right now. You're going to be having the opportunity to try to actually sketch graphs. And don't worry about like nervous about this. This is just an attempt. You're going to try to sketch them, and the answers are on the last slide or for you to check your sketches. And before you try out your skills, briefly share your strategies. So right now, when you were matching your cards, what was the strategy that y'all were doing? So everyone should be on slide 8 and just sharing what was your strategy. Maybe your strategy was checking in with me. Maybe your strategy was another thing. Like, what were you looking at when you were matching up these cards? Go ahead and type out your answers for slide 12. So we should be on slide 12. Take a moment for that. I'm going to try and see who we're missing here so I could prompt you to participate. All right, sorry y'all. Let's go ahead and see what y'all had as strategies. Oops, let me anonymize this again, sorry. So first one here has a lot of writing, and some of you are still writing. Go ahead and keep writing here. So my strategy was to do two things. First, look at how the original function starts and ends. If it starts positive, then the derivative graph will be on top of the x-axis. If it's negative, then it's going to be below. Then I looked at whether the maximum/minimum on the function graph matches where the derivative graph touches the x-axis. I think that's an awesome strategy, to be honest. It's actually something very similar that I do too when I look at these. All right, Felix was also, so one of the things looking at was where was the line crossing the x-axis or where the curve was crossing the x-axis. Oh, okay, I used the example you used with Juan's match and applied it to my own matching. I also used trial and error. A lot of you are looking at the minimum, the maximum, increase and decrease, and where it crosses the x-axis. Awesome strategies. Or personally was trying to match the graphs which I thought were opposite. Noticing where the graph was increasing or decreasing, following a pattern of when the original was decreasing and then the derivative was below the x-axis and the other way increasing. Doing trial and error and then needing to attend office hours. Yeah. Tomorrow I have office hours at 10. I always have them Monday through Wednesday. Awesome though. But so far, I mean, hopefully these strategies are helpful as y'all are looking at this. All right, we're gonna just do one challenge problem and then we'll check out the answer just because we need to move on with the big ideas for this. So let's do it. So challenge one, your job as students will be to try to actually sketch the derivative of this function. Now, as a tip, usually the derivative functions are smooth, right? They're smooth and curvy like a polynomial. The only time there's like a not smooth thing is when there's corners in your graph, but this one doesn't have any corners. Again, the strategy to do or to use is I like to imagine that I'm drawing tangent lines on this curve. Like, okay, I know that the tangent line slope is is negative here, and it's negative here, continually becomes negative, negative, it's going to be 0 right here. Then it starts to go positive. The derivative slope is positive. Then it's going to become 0 at the maximum. Then it's going to become negative. So that's how I like to look at it. I like to just trace and imagine I'm drawing tangent lines to this curve. Remember, tangent means it's just touching your graph at one spot. And these are messy tangents, but basically it's recording the behavior of my graph. So I notice that at first, and I like to draw these dotted lines. I do my dotted lines to kind of separate where the minimums and maximums are. Separating these. So, because when you do that, you can easily see that before, like for example, before a min or a maximum, it's either increasing or decreasing. Right here, the slopes are negative because it's decreasing. Right here, the slopes are positive, so it's plus. And then right here, the slope is negative because it's going down. And then remember, when it's negative, your original graph is negative. That means derivative graph is below the x-axis. So that's over here when it's negative. And let me make this small. And then when it's positive, that would mean the derivative graph is above the x-axis. That's exactly the tip that Pierre gave us. And it's also one I mentioned, but that's the one that Pierre was using. That's for the middle part. When it's a positive slope, that means the derivative is above the x-axis. Hopefully y'all are starting your drawings as I'm typing this. And then again, when it's back to negative, the derivative goes back below the x-axis. So those are some tips on how to kind of sketch your graph. I'm excited to see what you all are doing in your sketches. Oh yeah, by the way, you can already start sketching. You just draw. You click on the tool and you start drawing. Sorry if I didn't mention that. You can already start drawing. All right, we should all go on slide 13, y'all. I see 11 of us on slide 13. Awesome. And you're just trying to sketch, and we're going to take a look at what y'all came up with. All right, let me clear this up so I could see what y'all are coming up with. Okay. Make sure you get your sketches in. So I see right here, Gregory has a line. Pierre has kind of like a upside down parabola. I noticed a similar kind of parabola there with Alan. And then Diana there is using the strategy of kind of trying to match up where the maximums would, intersect the x-axis. And it's okay if you don't know, just try a sketch and that's fine because we're going to look at the answers later. I mean, right after this one. Ooh, I love that. I love how Alan is doing annotations on the graph, like showing where it's negative, positive, negative. That's awesome. It's very beautiful. Oh, and I see Emil. I think that's how you say Emil. First starting off by putting two intersecting points there where the maximums and minimums are. That's a good strategy to start there. And we're missing Felix and Emery's attempt. And it's okay to be wrong. You don't have to worry. And I'm not sure if Mary Ellen is ready yet. Hmm. Oh, it doesn't let you put next because I paused the screen on this one here. Because after this, we're not going to do the other challenges. We're going to jump into the answer for this one and so forth. All right, we got an attempt there from Felix. Then I also see Ed Ray started by putting dots there where the maximum and minimums are. Diana has annotated the graph nicely as well, kind of like starting off. Ooh, I like that. Like it's negative, so I see there's a line below the x-axis. Where it's positive, there's nothing, but I notice there's when it's negative, there's a line down. That's a great start. Again, for those struggling, I definitely use these annotations that it really helps. If you break up your graph and then identify where is the tangent line slope negative, that means the graph is below x-axis. Where is the tangent line's derivative positive or increasing, then your derivative graph is going to be above. And then where it's decreasing, the line should go below the x-axis. So that was a good, it's a good tool. And I see two students are using it. All right. Thank you all for your attempts. Let's go ahead and jump into the answers, which is going to be, where's our answers? I don't know if y'all can see it. So don't do challenge 14, 15 because we don't have time, but okay, so the answer to this, you could just check out my screen. You don't have to follow me because we're skipping to. The answer is this. Yeah, this is the answer to the derivative match, the drawing that you all did on number 13. So yeah, so a lot of you were very, very close. Yeah, pretty good. Awesome. So that's how the graph should look like. And we're going to go ahead and synthesize this. So right now for the synthesis, this is going to be the end of the Desmos activity. We're going to synthesize the big ideas so that you know kind of like how to start these. And if you're having difficulty with this, office hours tomorrow at 10, because this is hard. This is not easy. So this is a challenge. I'll say that. Let me go ahead and go back to our slides. Y'all can go ahead and close up your Desmos. Don't worry, it saves all your work. And we're going to go back to our slides so we can now start writing down the big ideas, the important key learnings from this. So let's transition right here. All right, so the big ideas, and this is going to go in our big ideas packet. So please have paper, or if you're doing digital notes, go ahead and do your digital notes in a Google Doc. You could take screenshots and take your notes that way. But here we go. Whenever your original function has like a smooth maximum or minimum, your derivative function has a 0. That means intersecting the x-axis. Here's an example. This is the one we kind of talked about before, but again, at these two locations, right here, where there's a minimum and also where there's a maximum, corresponds to a 0 in the derivative function that's in purple. So that's a visual to kind of help you see what I mean when I'm talking about this bullet. And a lot of you were using that big idea when you were putting the dots on your graph. You were kind of already using that. Like you knew that there has to be a 0 there in the derivative graph. You don't necessarily have to write down the visual. If it helps you, go ahead. But you just need to write down the bullet point. These visuals are going to be present in your big ideas packet as well. And it's also on my slides. You can always go back and check it out. Let me give you all a few seconds to at least get the bullet in. And let me know if anyone has questions, by the way. I'm happy to clarify any of these bullets. So this one's a huge, big idea. It's a great way to help you match. Again, whenever your original function has a minimum or maximum, that corresponds to a 0 in the derivative graph. And the 0 means it's intersecting the x-axis at those points. Okay, I'm going to move on to the next one just so we could cover this before I check out. The next one, and it's okay if you didn't get the pictures down. When the original function is horizontal, your derivative function is 0 during that interval. What do I mean by that? Here's a picture of that. So notice the end behavior. That was what they were asking about. Like notice how it flattens out at the ends, and notice how those purple dots are basically on 0 on the x-axis. When the original function flattens out and becomes horizontal like so, notice that the derivative function is becoming or is 0 at those locations because the tangent line is going to become horizontal if you draw it. So that's another tip there for when you're doing your sketches or when you're doing matches. Let me leave this up for like 30 seconds there. Again, we'll have this in the big ideas packet with the visuals, and you have these slides on Google Classroom too. All right, so that was big idea two for this. Whenever your original function flatten out or become horizontal, your derivative function is going to be 0. That means it's touching the x-axis, as you can see in the purple dots. Next one. Whenever your original function is increasing, the derivative function is above the x-axis. And that makes sense because the derivative is positive. Whenever your original function is increasing, the slope of the tangent line is positive. A correlating big idea to that is the opposite. So vice versa, when your original function is decreasing, the derivative graph is below the x-axis. And again, that makes sense because the derivative is negative. That means the y values are going to be negative. And here's the same visual example for that. And it's that same strategy that I've been using. My go-to strategy is I draw dotted lines where the original function either has a maximum or minimum. And by doing so, I kind of break up the increasing and decreasing intervals of the function. So right here, my function is increasing. The original function is going up. It's increasing. So I put a plus. Notice how that corresponds to the derivative function being above the x-axis in purple right here. The derivative function in this middle part is now decreasing. So therefore, the slopes are negative. And notice how that corresponds to the derivative function in purple being below the x-axis. Then my red line starts to increase. That means the tangent line slope is positive. And again, notice how that correlates to the derivative being above the x-axis. And this is our x-axis. So those big ideas, these ones here are very huge too, because those are the strategies we're using to match not only where the zeros are, but the behavior of your function. I'll pause at this point. Let me know if anyone has any questions. Then we'll do our quick checkout. All right, I hope you all got this down. And if not, don't worry, it's on Google Classroom. Today I'm not collecting notes, but it's totally helps for you to write it down so that your mind, it kind of gets soaked in there. It takes repetition to get the understanding in. Literally, I think it takes like 7 times for you to do something before it actually starts to hit your memory. So that's just some tips there. So we're going to finish up the rest of the lesson synthesis, which is, the corners part, in our next class on Thursday. And let's jump into our checkout. And this could be anything. What information can you tell me about the derivative? And again, as a reminder, what we were doing right now in Desmos is we were trying to graph derivatives using an original function. But what can you tell me? And it could be anything. It could be what you know about power rule. It could be anything related to the tangent line. What do you know? And it could be surface level. All right, so here's our first one. The derivative will be positive when the function is increasing. Yes. It is the instantaneous rate of change. Yeah, the derivative has so much stuff to it. Let's keep this going, y'all. Those are all very true. The derivative is like packed full with stuff, and it's also useful in so many applications in like physics and more, like electrical engineering or even mechanical engineering. All right, let's keep this going. So what information can you tell me about the derivative? And it could be very basic or it could be very deep. All right, we got some more stuff here. For surely. The derivative have points of 0 when the slope is horizontal. I love that. And I love that because it's not just saying, oh, there's zeros when there's a max or min. It's like there's that understanding that you know that the tangent line has to be horizontal. So I love that one. Where the tangent line is horizontal, the slope is 0. Wow, you two kind of had the same train of thought there, because I had a private message and then there's a public one. The derivative shows how the slope on the tangent line changes. Yeah, it does. And that was a question. Like someone asked that a question, but that's true. The derivative does show how the slope on the tangent line is changing as you're tracing the graph. That's true. Oh. The derivative shows how the tangent line shifts more upwards or downwards. When the slope is linear, the tangent line is straight. Yeah, you saw that right on the Desmos activity. When the original graph was a line, the derivative was a straight constant. That makes sense because the slope is constant always for a line. It's never changing. The derivative shows the change in slope of the graph. Yes, so powerful, y'all. All right. So tonight, y'all, we have an asynchronous assignment due. If you're struggling with that, jump into my office hours tomorrow. But otherwise, you're not going to be marked wrong. You just want to try it. You're going to get your full credit. All right, everybody. Y'all have a great day. Bye. Hope you all had a good day of maths, hopefully. Bye.
Yeah, so would it be okay to come to your office hours tomorrow and turn the homework in tomorrow?
Yes, it's totally okay. Yes, I'd love that.
Okay.
All
All right.
right.
Thank you.
You're
Bye.
welcome. Bye. Bye, everybody. I'll try to get this recording in.